Let's go back to it, shall we? What do you call a pig? These are good though. Like, I don't want to change because I might miss all the good jokes. Okay, so as we get into our second mixed rider example, again, our thinking is really around getting into these diagrams that start looking fairly complicated. So I think the real challenge is just spend a little bit of time getting to grips with the diagram before even worrying about all these questions over here. So AB is a diameter, in other words, it's a straight line. So if that's a diameter, we already know that there's a nice angle in a semicircle that is 90 degrees. We also maybe know that looks like a radius, that's a radius, so we've got an isosceles triangle over here with those two angles equal to each other. This here tells us that OB, or maybe just even OP, is perpendicular to that, so therefore we already know that that's equal to that because line drawn from center perpendicular to a chord bisects it. So there's some things that we can see, and there are going to be quite a few others. There are probably some angles in same seg. I don't know, from C and B. So if we start from C and from B, we can go across to D, so that will give us one angle. And if we also start from C and B, we're going to get another angle over there. Those two must be the same. Oh, there's probably an angle at center as well. So starting from C and B, let's actually capture that here. We can go to the angle at the center, so this angle's twice either of those two. Okay, so as I say, kind of things we're just getting into from the diagram. I don't know what else kind of jumps out in this diagram. I don't know what else. Chord cuts, proof. Okay, and a lot of these things here are basically telling us that, things that look like straight lines are, that is a straight line, that is a diameter straight line, these are straight lines, that's a straight line with that on it. So this needs to be captured in some way up here. So let's see what we need to prove. CBP, so B1 is equal to DBP. So those two are the same, these two over here. Okay, so we could do this in a few different ways. We've got a 90, we could, don't sell yourself short if you're going for some similar triangles and congruent triangles and that, because there probably are quite a few similar triangles. This is a 90, and this triangle probably ends up being similar to this triangle. I don't know. That feels like maybe a roundabout way to do it. But if you're thinking similar and congruent triangles, keep those thoughts in mind. They may not apply right now, but they are going to come in hand quite a lot. Okay, so those two are equal. Let's just revise here. So we know that we know that all of these are 90 degrees. So that's 90 degrees. So that's 90, and that's 90 over there. And we know that this is 90 up here as well. So maybe let's work in this big triangle up top here to say, well, in that triangle up there, this angle is equal to this angle. We saw angles in same seg. So if that is the same as that, the other one's 90, the third angle in the triangle must be the same. So let me just let me highlight this other triangle. So if we look in this triangle over here, I'm actually thinking of proving similar triangles here. So if we've got, a 90 in the red triangle, which is up top up here at C, and this P over here is 90, we know that angle A over here is equal to angle D, then the last angle in the triangle must be equal to each other. So I don't know, that's one method that's come out now. You may have had a shorter, quicker way to do that. That's, seeing as I was rambling away about similar triangles, that seemed to be one way to go. So I'm always interested all years if there's another way. I don't want to, do you want to look for other ways to do that? We could do, maybe if B2 equals x, then this one, hold up here is x because of angles and same seg. Maybe that would be one way to get there. If B1 is x, then this is 2x over here. So that could help us definitely. And maybe then this is x up here because of exterior angle of triangle. And then you've got, I don't know, lots of different ways. I'm not too caught up, and I don't want you to be caught up at this stage of just, oh, there's only one way. Like that's the beauty, is that there's so many ways. So out of all of that, we've got that that's x and that's x, and we had a few 90 degrees, and we knew there was a 90 up here. Prove that CED. So let's rewind on our colors and get some more going here. CED, oh, that worked really well. We'll get there. CED, so this one over here, that one over there is equal to twice CBO. Now CBO is x. So in other words, what we're required to prove is that this is x. So we need to prove that CED equals 2x. So at some stage in this first one, it would be nice maybe if you said, let one of these CBO, let's make sure it's the same one, why not? Let B1 equal x, and now we can just refer to that as x, and we just need to show that that's 2x. Okay, well, again, going to be quite a few ways. We said that we noticed earlier that there was an isosceles triangle over here, so may or may not be useful, but, there might be an x up in the corner over there. So if that's x, and then we're trying to get this one here. Now, just maybe a word of caution in case you're going there to going, oh, well, maybe this 90 is useful because from A and D you can, or from O and D, or C and D. If we're going to use angle at center as twice angle at circumference, just remember we need to kind of start from the circumference. So, I don't want to ever talk about going from O and C and kind of subtending an angle like that. None of our theorems work like that. None of our theorems say you start like that and subtend an angle. So as you're looking down around your diagram, it's always going to look like that. And it's never going to go to a random point in the circle. It's always going to go to the center, or it's going to go to the circumference. Okay, so just things to maybe watch out for. So if we look here and kind of look back at our diagram to go, okay, so we've played with a whole lot of ideas, but let's rethink how we were looking earlier and say, so this angle CED is created or subtended by going from C and D. Maybe I should move here. I'm in front of D. So C and D kind of subtend that angle. So let's see if we can subtend any other angles from C and D. Well, we can. We can go to B. Oh, wait a second. That angle there, if we subtend it as 2x, and those are angles in same seg, so that angle at E must be the same. Hey, it must be 2x. In other words, it's 2x. That's what we're trying to prove. So out of all of that, all we needed was just to go across to B and to E, angles in same seg. Okay, so if we've got that now, let's put that in our diagram. I'm going to rub out these things we don't need. So here we go. Come on. There we go. So this angle here is 2x. We know that x, I don't know if we're going to need it, but I'm just going to leave it there for now. Third part, CEFO is a cyclic quadrilateral. So let's highlight our cyclic quadrilateral. CEFO. So if we do that, and that, we need to prove that it's a cyclic quadrilateral. Now, there are two ways that we're going to do that, right? So if we're going to prove it's a cyclic quadrilateral, well, three ways, but the other one's kind of the same. We're either going to show that opposite angles add up to 180, or we're going to extend one of the lines, and we're going to say that the exterior angle, this doesn't look like a very cyclic quadrilateral. So let's just do a quadrilateral that may actually be cyclic. Those both look up. No. Well, let's just say that one. So if we extended that out, we could show that exterior angle. Oh, I'm in the way always. So we could show that exterior angle is equal to opposite interior angle. So that's the second method. And the third method might be that we can show angles in same seg are equal to each other. Any of those options will do. And as always, one or more of them may be possible. So in this case, we've got our quadrilateral here. Now, the way that comes to me at the moment, and this kind of always feels like it changes each time. Like maybe the next time you do it differently. I'm going to extend this line out to go for an exterior angle and hopefully prove that that O2 is 2x. So I'm going to put a 2x is what I'm hopefully going to prove. Well, if we kind of looked at this earlier and we said, well, if we go from A and C, we've got an angle at the center, and we know that the angle at the center is twice the angle at the circumference. So then that works. We could use that reason to say O2 equals 2x, angle at center is twice angle at circumference, therefore cyclic quadrilateral because exterior angle is equal to opposite interior angle. So, I didn't want to just run through and say, here's one way of doing it. Hopefully that gives you an idea if you needed to go through and just grapple and play with the diagram. You may well have done things differently. You may have done them quicker, more slowly. Doesn't really matter. What we really want is just play and grapple with those diagrams and make sure that for every statement, you write down a reason. So with that in mind,